Hello. Good morning, everyone.
Good morning, sir.
Yeah. So I think we will wait for 5 more minutes so that more student can join. Okay. Then we will start the session. Hello everyone. Yeah, I think we can start. So today's outline of the discussion is first we discuss about the magnetic disk, then we discuss some numerical about it, and, okay, and then if you have any problem, then you can ask. Okay, am I audible?
Yes, sir.
Yeah. So, how many of you have watched the lecture 8.4? Please raise your hand. Yeah. Okay, I think most of you have watched the 8.4. So, okay. Okay, let me share my screen. Is it visible to everyone, right? Magnetic disk. My screen is visible to everyone, right?
Yes, sir.
Okay. So, what you know about the magnetic disk? Can anyone answer? Magnetic disk. When you heard about the magnetic disk, what is the pop up in your mind? So, what is that?
I'll try and answer. So, I mean, it's very similar to what you call those LP records, like CD-ROMs, with a magnetic layer on it, and then it's split into sectors and tracks, and it spins across spins on a spindle kind of a thing, with heads aligned to each of those disks. There can be multiple disks on a particular head, and sorry, on a particular spindle, and then the head kind of moves across the disks to read data of specific sectors.
Okay. So, okay. Once again, I will define that. So, magnetic disk is a secondary storage device. So, which is basically stores the magnetic material to store the information, right? So there is the magnetic disk. Now we will discuss about what is the diagram of the systematic diagram of the magnetic disk. So what is the diagram? We see the what mechanism it apply, how it is stored, and okay, and so we term see the term, right? So magnetic disk is a consist of the platter, right? So platter is a circular shape and the flat surface, which is generally made up of the some rigid material or the glass. And so this is the platter. Platter has the surface, right? This is the top surface, and this is the bottom surface. So this surface is covered with the magnetic material. So that is basically used for storing the information, right? This material are used. So in a magnetic material, magnetic disk consists of 1 to 5 platter, right? So these are the platter, right? And platter is mounted on a spindle. So this thing is known as a spindle. Okay. So this is the platter up to this. This is a platter, right? And this is a spindle. Right. So this is a side lateral view. If we see the top view, okay, so it's look like this is the surface, platter surface, right? This is the top surface, and if you look, this is the spindle, right? Is it visible or understandable, right? This picture, or shall I draw it? Okay, let me draw. Okay, yeah, let me draw. Right, this is the plater, and this is the spindle, right? And this is the top view. Okay, so plater is for read the information from the plater, we use the read write head. So this is the read write head. This is used for read the information from the plater, and also we can, using this read write head, we can also write the information to the this plater. Okay, up to this is clear. I introduced 2 or 3 terms, right? This is a read write head. The read write head is used to read the data from the plater or write the data to the plater, right? And I introduced the plater also. So plater is a flat surface, right, which is covered with the magnetic material. And I introduced the one term spindle, and the spindle is uh, where we mount in the spindle, we mounted the plater, right? So this spindle is moved using some motor, or right, using motor. Okay. Okay, so this is the flat plater surface. This is the read write head. Okay, and after this, so this plater is logically divided into tracks. So tracks are, these are known as track, right? Circular track. So this is logically divided into. So this is the tracks, and tracks is further subdivided into sector. So we know this thing as the geometry center. But in the DBMS, we particularly, this particular portion, right, is known as the sector. Right, this is the sector or sectors. Do not confuse with the geometric term. So geometric term, we, this is known, this whole thing is known as the sector, right? Yes or no? Hello, am I clear up to this point, which is the sector? So do not confuse with the geometric center and the what you are using in the sector term in use in DBMS, right? So this particular portion, so suppose this is known as the sector, right? So this is the smallest unit of the magnetic disk, which is generally used for the to write the data and read the data from it. So whenever you want to read some data from the magnetic disk, so this is the smallest unit, we refer this the sector, right? Okay, so I have shown you that there are several platter in the magnetic disk, right? So this is a spindle, and each platter has the, if the surface not mention about the surfaces are used, which surfaces are used for the storing information, then you by default you have to assume that the both surface of the platter is used for storing information, right? So this side is also used for storing information, and this side is also. So in a platter, both the surfaces are used for storing information. If it is not explicitly given that the one-sided platter is used, right? So by default, you have to assume the both surface, right? So each surface has its own read-write head. So this is the upper surface as this read-write head. Lower surface is also has the read-write head. These are the read-write head. Okay. And these are assembled into and attached to this ARM assembly. Right. Okay. So whenever this ARM assembly is this read-write head are moves only this forward and the backward only. The forward just to go that if you want to read the information from this track, then it will move forward. Then if you want to read the information from the outer tracks, then it move backward, right? So only 2-4 motion is there, 2-4. Okay. So
The
every
discs
time
can individually rotate, is it? As in they'll all rotate only in sync, or can they rotate?
Yeah, they move in sync, right?
Okay.
Yes. Yeah.
So if you read from sector 1, let's say some arbitrary number, sector 1 in disk 1, the second head can read only from sector 1 of disk 2. I mean, sector 1 as in the corresponding sector only.
Can you repeat your question?
So what I'm saying is, let's say the topmost disk is disk 1. Okay. And top
platter 1.
Yeah, this is 1, then the next one is 2 and 3 and so on, right? A platter 1, platter 2 and so on. Okay. Right. And then if I have a head which is positioned against sector 1 of platter 1.
This one.
Yeah.
Okay.
Sector 1 of platter 1, then it will be only sector 1 of platter 2 also that I can read, right? If it has to read the head of the second platter, the head that is against the second platter.
Yeah, this one.
That will be aligned to sector 1 of platter 2, right? Meaning sector 2 or sector 1 of platter. I mean, they'll both the disks have to rotate in sync only, right?
Yeah.
Okay, so assuming I have some hypothetical numbering, then it will be the same sectors in all the plates, all the platters that the head is positioned against.
Not same sectors. It's supposed some information you want to read, right?
Right.
Okay. So this is suppose here this is diagrams. Suppose you want to read this sector, right? So some information you based of you move this all the platter depend upon this read write head only.
Right.
Hello.
Yeah, got it.
Yeah. So you look that's the if this particular read write head want to read from this ith track, right? So all other tracks, all other read write head are on ith track only, right?
Okay, that's what I wanted. Okay.
Yeah, and these things is known as the ith cylinder, right? We refer this all the ith track, all the read write head in the ith track is referred as the ith cylinder. So it's look like cylinder, right?
Like a logical cylinder.
Yeah, logical. Yeah. So this thing is also clear to everyone, right? There is the term or the likes the platter and surfaces, which is the surfaces, and which is tracks.
Sorry, sir. Surfaces is surface is this?
Surface is this is the platter, right? This is the top surface and this is the bottom surface.
Okay. There are two surfaces. Okay.
Yeah.
Purple.
And sector. Right. Okay. So now we will see what is the measure of the performance measure of the magnetic disk, right?
Sir, how track or cylinder will be same, sir?
Numbers of cylinder and the track are the same, right? You want to ask that thing, right?
Yeah, yes, sir.
Yeah. So this is suppose this is the first track. Okay.
Yeah.
This is the second track.
Hmm.
This is the third track, and this is the fourth track. And what is the definition of the cylinder? If one read write head is the ith track, all the read write head is the ith track, right? So that things is known as the
Cylinder.
ith cylinder, right? So this is if there is the one platter also. So this is the first cylinder. This is
sir.
the second cylinder, and this is the third cylinder, and this is the fourth cylinder. You can see as the
The view
numbers
will
of
be changed, right, sir? The dimension. I mean,
which
we are seeing upside means that will look like a track, like we will see.
no, this is we can from the upside we can see these are all logical. These are not physically divided. Yeah. So you can assume when you can see this thing from the side, this view, so side view, then we can see this is the ith cylinder, right? And when you are see this is from the top, yeah, that is the track. You can see.
Okay.
So how this thing is the numbers of track equal to numbers of cylinder.
Okay, sir. Thank you, sir.
And now we will see the performance measures of the magnetic disk. The first is the capacity. And second is the access time. And the third is the data transfer rate. And the four is the MTTF. The full form of MTTF is the mean time to failure. So we will check one by one each term. What is this term? So first we will see what is the capacity. Right. So capacity is the amount of a data can be stored by this particular magnetic disk is known as the capacity of that disk. Right. So suppose you have given like that. The magnetic disk consists of the 5 platter. So I am telling about the specification of the magnetic disk, right? Specification, right? So number of magnetic disk is not magnetic disk, numbers of the platter is let's say this is the P, right? And by default you have to assume that the both surfaces the encoded, right? Encoded means storing the information, right? Okay. and the numbers of tracks per surface is T, suppose, and the number of sectors per tracks per track is S, right? And size, the sector size is given, suppose 512 bytes, right? So you have to calculate the capacity of the magnetic disk. So how you can find that?
So, but sector size is not fixed, right? Or because outer tracks will have larger sectors, no? Or because of the size?
No, you can say this is the just for understanding purpose, but in the practically, these tracks, these are the stored the less numbers of the track, less number of sector contains the less numbers of sector, and this contains is the more numbers of the sector. This is just for the understanding purpose. I just said in the, don't go with the geometric, right?
Okay,
Right.
no, I mean, just to understand, so sectors we are saying is going to be constant, it's going to hold some constant size, but there will be n number of sectors per track. That's what you're saying. Is that what you're saying? Like a sector will be a fixed size of 512 bytes or something.
Yeah,
there
yeah,
will be so many sectors per track.
yeah. So this is the built upon the numericals. So this in the practical, if I tell you what happened, so this is the numerical way, solve numerical this way. So everything we construct ideally, right?
Right, right.
Yeah. So that is the not in the practical purpose, right?
Yeah. So just practically, I'm just trying to understand whether even practically whether the sectors will have a fixed size, but it'll have more number of sectors in the outer tracks and less number of sectors in the inner tracks.
In inner track, right?
Okay,
that.
But the sectors will still have a fixed size, is what you're saying.
Yeah, yeah.
Okay, okay. Just that the outer tracks will have more sectors per track.
Yeah.
Okay, okay, sure. Thanks.
So the capacity of the disk, how to find? So you have given the numbers of platter is P. Okay. So given number of platters equal to P. So can you tell me what is the total number of surfaces?
2p. 2p, right?
Yeah, 2p, because the each platter has the two surfaces, right? Surfaces. Each platter has two surfaces, then total numbers is the 2p. Okay. So what is the total numbers of tracks? You have given the numbers of sector per surface is T, and total numbers of surfaces 2p. Then the total numbers of tracks is
2p.
2p into T, right? So everyone got it. If you have any doubt, you can ask, right? This is very important. Okay. Okay. So total numbers of tracks is that you have this is the total numbers of surfaces, that is the 2p, and then the numbers of tracks per surface is T, then the total numbers of sectors is the 2p into T, that is 2pt. Okay. Now tell me what is the total numbers of sectors? right? You got, this is given the numbers of sector per track, right? That is S. So you have how many tracks? 2pt. Then if we multiply with the S, then we get the total numbers of the sector. So that is 2pt into S. That is 2pts. Okay. Now each sector size is given to you. That is the 512 bytes. Right. So then you can tell the size of the disk is the numbers of sector, total numbers of sector into the sector size. That is 2pt into 512 bytes. Right. And that is PTS 1024 bytes. And everyone know, right? In 1 bytes, how many bits are there?
8 bits.
8 bits. Okay. And 1 KB, KB means kilobyte, right? Yeah, tell me, anyone, everyone knows, right?
1024.
Hello. How many bytes? 1 kilobyte.
1024.
1024 bytes, right? And 1 megabytes equal to
1024 KB.
1024 KB. And if you tell this thing in terms of the byte, then it is the
2 power 10 KB.
2 to the power 20 bytes.
Bytes. 2
Yeah.
power 10 kilobytes.
No, if we tell this one, oh yeah, that is 2 to the power 10 kilobytes.
Yeah.
You're saying that's, this is the 2 to the power 10 kilobytes, and this is the 2 to the power 20 bytes.
Yes.
Okay. So up to this is clear. This thing is everyone knows. If someone, please note it. Okay. So you get the size of the disk is 1024 bytes. Then we can write this thing as the PTS. If we change this thing into bytes, then we can simply write the KB, right? So PTS. This is the size of the magnetic capacity. So you got how to find the capacity of the magnetic disk, right? Okay. So next we will discuss about some, what is the access time. So access time is the, whenever any read write operation is issued, and the time when that data transfer begin, right? That the time, this time is known as the, there is the time gap between the, right? So time, the time gap between, right, when's the read write any read write command, or you can see the command, or the request, you can say the request is issued, and when's the data transfer begins. Right. So this has the two components, right? One is the seek time, and the second one is the rotational latency. Right. So let me explain the term one by one. What is the seek time? Right. So okay. So suppose here is your read write head, right? And you want to access, there is a one sector is there, right? You want to access this sector, right? So first you have to identify which is the correct track, right? So from here, it will takes the time to choose which is the correct track. It have to be positioned on the correct track, right? So you have you have to find first the correct track, right? So if have to moves from here to here, so this whatever's the time takes this moving from here to here, this is known as the seek time, right? Right. And after the correct, it finds the correct track, but the sector is present here, right? So if have the disk need to be rotated so that it can be positioned under this particular read write head, right? So this time, whatever its time takes to move from here to here, so that's rotational time is known as the rotational latency. Is it clear to everyone what is the seek time and what is the rotational latency?
Yes, sir.
Yeah. So access time is the total of this seek time and the rotational latency, right? So you can say the access time equal to seek time plus rotational latency. So we take the on an average. So this the average seek time is the half of the course seek time, right? And so rotational latency is the half of the total time take by to complete one rotation, right? So half of the, you can say that is time period also. So the time taken to complete one rotation. Okay. So I think this seek time and rotational is clear to everyone, and the access time, what is, if you have given the average seek time and the average rotational latency, then you can find the access time, right? Yes.
Yeah, why don't we consider the data transfer time also in this? Because
so here the definition is what, the time gap between the read write once the read write request is issued and the data transfer begins, right? That is the access time.
is there a difference between this access time and disk access time? Because in many places I've seen they have taken this data transfer time also.
So I think they use the read time as also as the access time including the access time, right?
So whenever we need to calculate total access time, then we can add data transfer rate.
Okay.
Yeah.
This access time is the time taken for the read write head to track the data. Access time of read write head. This one.
Hello. Yeah. Can.
why half of this for seek time and rotation? Why we are like multiplying it with half?
This is, we takes the average time of that.
Okay,
No,
average
this
time.
is the average sick time, not sick time. Sick time, I define you what is the sick time. If you take all total of the disk for all the data, then what is the average sick time? So this is the average sick time. Do not call.
Okay, okay. Since it is on both sides, so that's why like we're taking half of this.
Yeah. This is also the average rotational latency. And I already defined what is the rotational latency time and what is. So this is the average of, we take, this is. Okay. Now it is clear. Yeah. Someone asked that question, why we takes the half. So now we discuss about the third part, that is the data transfer rate. What is the data transfer rate, right? Data transfer rate is the rate at which the data transfer rate is the rate at which we read the information from the magnetic disk or write the data to the magnetic disk, right? That is known as the data transfer rate. So how we calculate the data transfer rate? So we find the inner track, what is the size of the track. So we can find the size of the, how many amount of the data contained by that track, right? Track, right? This is the one track. We can find the amount of data contained by this track, right? Can you find yes or not? Is there a way to find
size per sector? You need the
Yeah.
size per sector.
So if you know the this is the, what is the number of the sector in the one track, then you can multiply with the sector size, then you get this track size, right? So that is the amount of data contained by this track, right? Okay. And you also you have also given, if you have given the average latency time, right? Average latency time is the half of the time taken to complete one rotation, right? So can you find what is the time taken to complete one rotation? So simply, if you multiply the average latency time with 2, then you get the time taken to complete the one rotation, right? Yes or no?
Yes, sir.
One rotation is the simply if you multiply 2 with the average latency, average rotational latency. Okay. Right. So what is the data transfer rate? Data transfer rate is the simply the size means the data contained by the one track. right? So size of the track divided by time taken to complete one rotation. So that is the data transfer rate, right? So what is data transfer rate is clear to everyone, right?
So the time taken to complete one rotation will vary for read and write, is it? For read, there will be one time, and for write, it will be another time, is it? Because write might take longer than read.
Yeah, but if you have the so similar way, you have to it is given to you, right? So whether he requests for the read data transfer rate or the write data transfer rate. So practically it is, yeah, I know about the practically it is a different, but we only taken the ideal case. Here we dealing with only ideal case.
Okay.
Hello.
Okay. Yeah, got it. Thank you.
So after the that is one measure of the one performance measure of the magnetic disk is also that is the MTTF, right? MTTF is the mean time to failure, right? This is the on an average one disk can run without any failure. That is the time. So in this way, we can find the reliability of the disk, right? So this is the, you got what is the magnetic MTTF is the mean time to failure, right? So this is the average time on an average a disk is a run without any failure, right? So you can see by the definition, this is the definition of the reliability of magnetic disk, right? So suppose you have given the 100 set of the 1000 newly disk system. So this disk, one disk system consists of the 1000 disk, right? So this system consists of the 1000 disk, right? So MTTF is given to you like that. Right. MTTF of this disk system is given as the 1.2 million, right, hours. The definition is clear to everyone. You have given a disk system consists of the 1000 disk, hence the MTTF is given as the 1.2 million hours, right? So you can say that's the on an average one disk will be failure in
100 hours.
1200 hours, right? So how you can find that? So that is the MTTF of one disk. Right. So MTTF is clear to everyone, right?
Yes.
Okay. Now, any doubt in the theoretical part? So
could you
this is all.
explain MTTF once more, because I'm
Which one?
MTTF.
So MTTF is the any disk run without any continuously run without any failure. The time. So what is the average time of the one disk is run without any failure, right? That is known as the MTTF, right? So if you gives the MTTF, is the, suppose there is a bulb, right? Everyone bought the bulb, right? That is given the 1 year guarantee, right? So on an average, it will run means 1 year without any failure. That is the MTT of that bulb, right? Similar way, we also gives the MTT of disk also, right? So this is the given as the 1000 disk is a consist in a disk system, and the MTTF is given as the 1.2 million hours. So you have to find the what is the MTT of one disk, right? So you have to find the MTT of one disk. So that is the MTT of a whole disk, right? So you have, if you try to find the MTT of one disk,
Yes, sir.
that is the 1.2 million hours divided by numbers of disk, that is the 1200 hours. So MTT of one disk is 1200 hours. Okay.
Yeah, how is it like one disk and whole disk kind of how is it coming actually?
Yeah.
MTTF is my understanding is it is mean time to failure. So how a manufacturer normally defines it is like suppose he has manufactured say 10,000 disks.
Yeah.
He'll say mean time between failure is basically an average expected mean time to failure. So some might last longer, some might last lesser. He'll tell mean time to failure is this many hours.
Yeah, that is the exactly here. That's things. I define that things in a different way. Hello.
Yeah. So you mean to say this say 1,000 total 1,000 number
In
of
a disk system.
there? Yes. Okay. So total number of hours expected is so much. So divided by this much is the mean time for one disk.
Yeah. And now it is clear to everyone. So MTTF and
How is that again when we are coming to a system when you are talking about? Is it a number? Is it a system you are talking about, or is it?
okay? Let me tell you in this way. So suppose there is a server, right?
Okay.
Server using the disk system. This is the one disk, right?
Yeah, a server. Let us assume there are 5 disks in a server.
Yeah, 5 disk in a server. This is the disk 1. This is the disk 2. This is disk 3, disk 4, and the disk 5, right? So this is the reliability of this is the 1200 hours. Okay. And we copy the same thing, same data, exact copy of this data. So whichever data here is, so exact the copy of the same data is in 5 places, right? So if I want to serve you, right, that data, similar data, if you want to access the data, same data, this all are the exact same copy of the data. So this is D1 is same copy, D2 is D3, D4, and the D5, same data. And you want to access the data from this. So whenever you access the any data, so the data will be served from only one disk, right? So if this D1 got failure, then also I can serve you the same data. So you are unaware of that, the disk got failure, right? Similar, if this disk also get failure, right, then also I can serve you the data. If this is also got failure, then also I can serve the data. This will also, if got failure, right, then also can I serve you. And if this got failure, then I cannot serve you the data, right? So can you tell me now what is the average MTT of this whole disk system? One is this. And so then what is the total MTT of this? Means how much time I can, if it is failure one after one. So suppose this is run in the 1200 hours, then it, after that it got failure, means sequential failure, what I mean. So then you can set the total numbers of this MTT of this plus this plus this, right? I think now you got the idea what is my point.
So sir, in the above example, the 1000 disk system, it takes 1.2 million hours for the entire array to fail, right?
Yeah.
Okay.
That is means that you have run continuously without any failure. Right?
Okay.
Someone asked that question. Now it is clear.
Yeah, when we are considering the whole system, then I understood it. Thank you.
So, and theory is now completed. Everyone understood what is the theory behind the magnetic disk. A different term is there in the magnetic disk. So, if clear, then we can move to the numerical problem. So this problem is from the practice assignment. How many you have solved this question? And how many unable to solve this question? Any problem faced in this problem? Yeah, you can tell, just unmute yourself and tell if you have any doubt. Are you able to solve or not able to solve? What is the problem in this question? We can discuss about this problem, right? Any problem in understanding this question?
So this is just 10 platters, two sides each, 20 into 64 into 256 into 512, but 512 minus 4, right? For free system. So 508 bytes per sector is free space.
Yeah. So let me tell you this problem in this way. Suppose this is the one sector, right? So first let me read the problem. Consider a disk with the 10 platter, 64 tracks per surface, 256 sector per track, and the 512 bytes per sector. And each sector, the 4 byte per sector is a reserve for storing file system information. So formatting data. So question is how much free space is available for use in MB? You have to tell in MB, right? So here you can see this is the total 512 byte. And each sector is a reserve. This is the 4 byte, right? 512 bytes, and the 4 byte is reserved for the storing file system information. So can you tell me what is the total numbers of space is available in the per sector? That is the 512 bytes minus 4,
512
right?
minus 4, it is 508 bytes.
Yeah, 508. bytes is the available free space. Then you have to calculate only the how many numbers of sector in that disk, right? So you can find that thing. So number of platter is 10. So total numbers of surface, yeah, that is 2 into 10, 20. Okay. After that's the total numbers of tracks. Each surface has the 64 tracks, right? So total number of tracks is 20 into 64, right? So I would like to write this thing in the 2 to the power. So this is the 2 to the power 6 into 2 to the power 2 into 5, right? Is it okay? But I try to write. So 64 is the 2 to the power 6. Here 4 into 5, 2 to the power 4. This is the total numbers of the tracks. Fine. Are you got it or not? Are you able to follow me or? Yeah. Yes or no?
Yes, sir.
Okay.
Yes, sir.
Yeah. So then total numbers of track sectors. Here you get the total numbers of the tracks. So if you simply multiply with the 256, then you get the total numbers of sector. That is, this is 2 to the power 7, 2 to the power 8, right? So that is 2 to the power 8 into this thing, 2 to the power 6, 2 to the power 2 into 5. This is the total numbers of sector. Got it? Hence now you multiply each free space is available for each sector is this. Then you find the total free space in the that magnetic disk, right? So this is the free space. In the disk is the total numbers of sector into free space available in each sector. Okay. So that is 2 to the power 8 into 2 to the power 8 into 5 into 508 bytes, right? So that is 2 to the power 5, 2 to the power 16, 5 into, this is a byte. You have to write this thing in MB, right? So 1 KB equal to 2 to the power 10 bytes. Fine. Yes or no? 1 MB into 2 to the power 10 KB.
Yes, sir.
So you can say 2 to the power 20 bytes, right? So if I divide that things with 2 to the power 20 bytes, so 2 to the power 16 into 5 into 50. You can calculate and tell me what is the value. 2 to the power 20 MB, right? So you can calculate that is the 16, right?
158, sir. 158.75.
158.75
8.75.
MB. Yeah. So this is the answer for this question. Right. So for everyone, this question is clear, right? What is the statement of this question and how to proceed? What is the approach? Yes. So we move to the next question. Though, so this is the next part of this question. So how many bits are required for the addressing all the sectors? So you know about that. If you want to store 2-digit, 0 or 1, 2 numbers, right? So how many bits are required?
1 bit.
That is the 1 bit, right? And for the 3 number, or you can say the 4 number, this is the 2 number, right? For the 3 number, you can represent with 4 number. So suppose this is the 1, 2, 3. That is the 4 number. You can represent this thing in the 2 bits. And how that is? So 0, 0, 0, 1, 1, 0. If you change this thing in the binary, right? So we generally store that thing in the computer in the binary bits, right? So that's why I am writing this thing. So 1, 0, and this is the 1, 1. So to represent the 4 number, you can see there is the 2 bits are required. So write this. So this is the 2 bits we can replace with the 0 ones, and we finds the there is the 4 combination we can make it, right? That is, you can say if we want to represent the 4 number, right? So let me tell this thing in this way. So for the 2 number, you can represent that things in the 1 bit, right? For 4 number, that is, you can, that is in 2 bits, right? And for the 8 number, you can say that thing is the 3 bits we can represent, right? Hello? Yeah. So this is, you can see, this thing is simply the, we can, if we takes the log of this using base 2, right? So that is the same thing. You can see this is the numbers 8. That is the 8 equal to 2 to the power 3, right? And we can say this is the 3 bit is required to represent the 8 number. You are able to follow me, right? This thing. For the 1 bit, you can say the 2 number to represent 2 numbers, that is required 1 bit, right? For the 4 number represent, there is required this 2 bits, right? Up to this is clear to everyone? Yes or no?
Yes, sir.
Okay. So you can tell this thing as supposed to represent the n number, right? So this is the ith bit is required.
Yes.
Yeah. So we can take the log both side 2i. So you have the simple formula is there. If you find the total numbers of the sector, just take the log of 2 of the total numbers of the sector. You get the numbers of byte required for addressing that all sector, right? So I'm just telling this thing as the, for the, you have to calculate the ith value, right? So that is the simple log n divided by log 2. So that is the 2n. So this is the formula, right? So you have to find the I value, how many bits are required to addressing the all the sector. Sector is the n. So you already have the numbers of value. What is the value of n? So this is the total numbers of sector.
Sir,
Right?
we have to round up, right?
Yeah. It takes the ceiling value of it.
Seal value.
This is the upper value. Right. Now it is clear.
Sir, I didn't get this. So n is the number of sectors.
Yeah.
I is the number of bits.
So bits required to represent it.
Okay, so for one sector, it will be just 2 bits, sir. How does it work?
Or one sector?
If it is one sector, it's 0 bits. Huh? How does it
Not 0 bits. One sector, it is the 1 bit is required.
1 bit.
One number you have
To round up the
round up ceiling value. You have to take the ceiling value.
Okay.
There are 17 digits, normally 16 numbers to represent. We take 4 bits, right? If there is 17th digit, then we need an extra bit to represent that one number.
Yeah. So suppose there is the 3. Here, if you represent the 3 number, that is the same thing as the 4 number is represent. Then also it will take the 2 bits. Yes. If you take the log 2 of 3, that is the same thing as the log 2 4 closely. So if you calculated, can you tell me what is the value of log 2 3? So you can simple. So how this is built up, this formula is formulated, can you understand, right? So this is the formula. If you take the upper value, you get the numbers of bits to represent, right?
So one sector is just 1 bit, is it? Does that how
Yeah.
how I should understand?
For one number, there is required 1 bit, right? That is the trivial case. Hello.
Right.
Yeah.
No, I'm
Yes,
just
sir,
thinking. Sector means 1 bit, is it? So I'm just.
Not sector means 1 bit. Sector means sector is the unit. Then you read at a one time. So suppose you want to read from the magnetic disk. So sector is you can see this thing as a unit that you read at a time. Means
Right.
all the whatever's present in the sector you read or write all over the sector at a time. So each sector have an address, right? So you have to identify which sector. So unique number is there. Okay. So up to this is clear. Hello.
Yes, sir.
Yes, right. Okay. So we move to the next problem. That is also from the practice question. Consider you have a file named IITM BSc in your hard disk. The file size is 1000 KB. Seek time in your hard disk is read at 3 millisecond, and the rotational speed is given as the 30,000 RPM. RPM means revolution per minute. Okay, and the disk has the 200 sector per tracks, and the sector size is 512 bytes. So what is the transfer rate of your hard disk? So I will wait for 5 more minutes, and we discuss about this. What is the transfer rate? data transfer rate, right? So this is the size of the track and the time taken to complete one rotation. Then you can find the data transfer rate, right? So please try yourself. We will wait for 2-3 minutes. Please all of you try. Hello. Yeah. What is the answer?
Sir, is it third option, sir? 33.33 kbps. kbms.
33. Can you tell your approach? What is the approach you are?
Sir, the 1000 by 30,000 rpm, that will give you 0.033, but it is asked in this kbms, right? So we are by 1000, that will turn converts to 33.33 kbms.
So, okay. Let me tell. What is given? This is the file size, right? But I am asking about what is the transfer rate of the hard disk, right? So you have to remember that the file size is a different, right? Hence the hard disk is also different, right? So file is the individual file, right? In a hard disk, you can accommodate many files, right? Yes, sir. So that is the difference. But transfer rate is the completely depend upon the a particular hard disk, right? Every hard disk has its own transfer rate, right? So what I said that the data transfer rate is that you have to find the what is the amount of data is stored in a track, right? Okay. So here you can see the disk has the 200 sector per track, and the sector size is a 512 bytes. So now you can tell me what is the size of the track. Right. Size of the track is right, 200 sector per track. If you multiply with this sector size, you got the what is the size of the track. Size of the track means what is the amount of data you can store in that track, right? So you can simply multiply with the 200 with 52. So you got the track size, right? So now you have to determine what is the time to complete one rotation, right? Now you have to find the time to complete one rotation. So how you can find? Here it is, you have given the rotational speed is 30,000 RPM, right? So that means 30,000 revolution per minute.
With 3600 by 30,000, the time taken to complete one rotation.
Yeah.
I'm solving it to be 6 by 50.
So that is what is the value of that? So what is the so you can say this thing is also the time period. Also, this thing we calls that, right? So 30,000 revolution per 1 minute means 1 minute in 1 minute. Take 1 minute, right? You can say 30 revolution take 60 seconds.
Yeah.
One revolution takes
16 to 60 milliseconds.
60 into 30 this millisecond. This one, right? This. Okay, I will come to your point. So this many seconds.
Mm-hmm. Yeah.
So, and if we change this thing into millisecond, then we can multiply with 1000. Right?
Okay. Yeah. Got it.
That is the 2 millisecond. Now, right? So time taken to complete one rotation is 2 milliseconds, right? Taken, complete equal to 2 milliseconds, right? Now you have to find the data transfer rate. So that is the size of tracks. Size of tracks means the amount of data can stored by. Okay, hence this is the time taken to complete one rotation. Right. So what is that value? So this is the size of tracks. 2 into 512 bytes
by 2.
by 2 millisecond, right? So you have to see in the option also. So option, it is a given everything in the kilobyte per millisecond, kilobyte per millisecond, kilo, right? So you have to also, you have to change this thing also, kilobyte, right? So you know about the 1 KB equal to 1024 bytes,
Divided.
right? So we need to divide that thing.
So 50 KB per millisecond.
Yeah. So now you get the KB per second. So that is the 2, and this is 50. So you got the 50 KB per millisecond, right? Desist, I think now you got it.
Yes, sir. Yes, sir.
So the second problem is also related to that problem, extension of that problems. So consider the fact that the file data is stored. You want to store that data into the non-consecutive location, a non-consecutive sector, right? So how much time will be required to read the whole data, whole file after the read request is made, right? So now the read request is given. You have to consider the access time and the transfer time also. So that is your answer. You have to first find the access time, then you have find the transfer time also. So please try this question also. Yeah. This is the extension of this question. You can all take the screenshot of this. This is. So let me write. So what is the given? The file size. This is the revolution per speed, RPM. Everyone, please try this question.
Sir, what is non-consecutive sectors? Is it the alternate sectors or each sector on different track?
Yeah, you can think about that. You have to assume that for the each track, to access the each track, there has the individual seek time, individual. So the problem statement means you have to find the individual seek time, individual latency also, hence each block read time also, uh, data transfer rate also finds the transfer, and you have to sum up this. Hello. What is the answer? Anyone have tried? What you understand or what this problem means? Can anyone explain what you understand from this problem? Yeah, Lakshmi can answer how, what is the approach? So that is the correct answer, right? So let me tell you. So question is, consider the fact that the file is stored in non-consecutive sector. How much time will be required to read the whole file after the read request is made? Right. So consecutive, non-consecutive means, so in a disk there is a data is, it is explicitly given the non-consecutive sector, right? So for each sector you have to find what is the seek time and what is the, right, for each sector you have to find what is the seek time, right, what is the, right, what is the seek time, what is the rotational latency time, rotational latency, and what is the data transfer, what is the transfer time, right, data transfer time. So if you can, that is the meanings of the non-consecutive time. So that's why it is explicitly given. So you have to find what is the seek time. Seek time is given to you for each sector, right? That is 3 milliseconds. And the rotational latency is also, rotational latency is given to you. No, you have to given that's the 30 revolution per minute, but we already find that the what is the time taken to complete one rotation, right? So we already calculates the time taken. Complete one rotation, right? So that is 2 milliseconds. And if what is the, then what is the rotational latency?
1 half into 2.
Yeah, half. That is 1 millisecond, right? So now you can tell me what is the access time to for one sector.
4 milliseconds.
Yeah, 4 milliseconds, right? That is the 4 milliseconds, 3 plus 1, 4 milliseconds. Now you have to find what is the transfer time. So transfer, you have already finds what is the data transfer rate. Data transfer rate is, you finds the 50 kb per ms, right? So that is your data transfer rate. Data transfer rate is 50 kb per ms, right? So what is the transfer time? Transfer time is the total file size divided by, if we divided by data transfer rate, right, then we get the transfer time. Yes or no? Right, and that is given 1000 kb. And this is the 50 kb per ms, right? So that is the 20 ms, right? So that is the transfer time of the whole file. This is the transfer time of the whole file. We get the transfer time of whole file, that is the 20 ms. right? Means millisecond. You have to, and we already gets the access time for one sector. Right? We have to find the access time for all the sector, right? So how to find that? First, we have to find what is the numbers of sector are there for that file. For that file, how many sector are allocated, right? So we have to find the numbers of sector. So what is the file size? File size divided by sector size. So that is the 10 KB 512 bytes. So 10 KB, if we return KB as the byte, that is the 1024 bytes, right? And this is the 512 bytes. Okay. That is the, this is the total numbers of sectors in that. This is the total numbers of sector allocated for that file, right? This many numbers of sector, and we already find the what is the access time for one sector. Access time for one sector. One sector is 4 milliseconds, right? So access time for this many sectors is 4 into that millisecond. That is the 8000 millisecond, right? This is the total access time for whole, right? Whole file. And what is the, and this is the transfer time for the whole file also. So this is the total access time. We find that 8000 millisecond, right? And this is the total transfer time. So if we add this thing 20 millisecond, so then we got millisecond, but answer is given in a second, then you have to divide it into, divided by 1000 seconds. Okay, everyone got it, right? Yeah, those who have does not got it, so you can repeat or replay to this session. So there is one important topic is the buffer replacement policy. So I would like to discuss about it. So anybody know about what is the buffer? So you know about the secondary storage, the main memory, and main memory is the RAM, right? And what we have already discussed about the magnetic disk, and there is also hard disk, right? So that all are the secondary storage. So this is the primary storage. We also say the RAM, main memory, right? And this is the secondary storage. So whatever we want to run in the computer, that bring into the means bring that things into the RAM and we execute it, right? You got some idea about how the program is run. Whatever data is present in here, means main disk, we store the data. The whole database is stored in the secondary storage, right? So we bring that data into the RAM and execute it. So that is the very time consuming. This is the very first, right? And this is a very slow with respect to the RAM, right? So what RAM will do? RAM will have some space. You can say that as the buffer, right? So it reserves some place for it, and it stored that disk information. So whenever you want to run something, right? So it first check in the buffer, right? Then if it's not present, if it is not present here, then it refers the secondary memory, right? And we replace if the space is not available here, then it is replaced from here. The data is replaced from. So this is the, and that things is known as the buffer replacement policy. So this follow the several procedure. This is the least recently used policy. The whichever data that is present here buffer, so that is least recently used, then we remove from the buffer and replace with the new data. New means you can say that as the block, new block, right? Right. And one is the MRU. So these are the policy how you like to replace here. So this is the most recently used. Whichever the data is most recently used, then you want replace that thing, right? And one is the FIFO, the first in, first out, last in, first out. These are right. These are some buffer replacement policy. So now in this problem, we will discuss only on the LRU. That is the least replacement, least recently used, right? You got idea, right? What is this problem means? Consider a string pending the block reference in the given 3, 4, right? So 3, 4, 1, 4, 2, 3, 1, 4, 2, 3, and the system has the buffer with the 3 slot. So that means the system has 3 slot here, right? So if you want to read this data from here, if it is present here, that means that is known as the hit, right? It is already present here. If it is not present here, then we go for the secondary memory, that is known as the miss, and we replace the, if it is empty, then we can simply place here. If it is not here, then we can replace, we need to replace, right? So if LRU buffer replacement policy is used, then how many misses will be occur while referencing all the requested block? So these are the requested block 3, 4, 1, 4, right?
So can you repeat hits and misses?
Hit is, suppose the processor requests for the one block, right? You want to execute that things. If that is present in the buffer, so here it is given the buffer with the 3 slot. So if the value is present here in this 3 slot, right, then you can say that is the hit. If it is not present, then you can say that is the miss, and you try to bring that data into this buffer. So how this will happen, we will see with this example, right?
Okay.
And we will discuss with this particular replacement policy that is least recently used. So how this is, let me tell you. Okay. So in the problem, it is given, there is the 3, right? 3 buffer, right? So let's take this is 1, 2, 3, 3 buffer. So suppose you searching for 3 in the buffer, it is present in the buffer or not? You tell me.
No.
No. that means that is the miss, right? So you want to bring that things from the secondary storage and stored in the buffer. So what that means, you store that things in the buffer, bring the data, put it into the buffer and execute it, right? For the future reference, you can directly go to the buffer if it is present, then you can simply execute from here. So yeah, so next entry is 4. If 4 is present in the buffer,
No.
no, and there is available place also, so we can place here also, right? 4 is placed in the next slot, so that is also miss, right? And after that, 1 is present, no, so we put it into the buffer and that is also miss, right? Now next entry is 4. Is 4 is present?
Yes.
Yes, already it is present. So this thing is known as the hit, right? Hit. So already present in the buffer. So no need for the replacement. So this is this right sign is for the hit, right? And after that, the 2 is present here in the buffer.
No, sir.
No. So we need to replace it. So which one? So what is the replacement policy here? That is the LRU buffer replacement policy. So which is the least recently used? The element present in the buffer, which is the least recently used. Here you can see 4 is used, 1 is also used and present in the buffer. 3 is the least recently used. So we can replace with the 3. 2 is replaced with the 3, right? And that is also miss. Okay. After the entry 3, whether 3 is present here? No, in the buffer. No, so we need to replace it. But which element is used for replacement? So which is the recently used? 2, 4, 1. 1 is the recently used. So we replace with 1. 3 replaces 1, right? So that is also miss. And again, after that, okay, let me write 1, 4, 2, 3. Okay. Okay. After the next, your request for 1. 1 is present in the buffer? No. So we want to replace that things with the 4. 4 is recently used. So that is the 2, 1, 3. So that is also miss. After that, 4 is not present in the buffer. So we replace of 2. So that is 4, 1, 3. That is also miss. After that 2 is present, not. So we replace 3. Right, that is also miss. After we looking for the 3 is present here in the buffer? No. So which element to replace? 1. So 4, 3, 2. So that is also miss. Now can you tell me what is the numbers of miss and hit? So this is the one miss. 1, 2, 3, 4, 5, 6, 7, 8, 9. So number of misses equal to 9 and number of hits equal to 1. Right. So I think is LRU is clear to everyone. And what is the buffer replacement policy? Yes or no?
Sir, there is no difference between LRU and FIFO, sir. Practically, because FIFO is also the first in, first out, isn't it?
First in, first out, right?
Yeah.
So yeah, let me tell you in this way. Here you can see the difference here. I think we somewhere okay, we can try also with first in, first out, right?
Yeah.
Yeah. So there is difference. Okay. 1, 2, 3, right? So here you can see first three is present, not. So that is miss. 4. 4 is also not present. That is miss also. Here this is the LRU, and you tell that's the first in, first out.
Correct.
Right?
Yeah.
First in, first out. Okay. So 3, 2. Okay. After that 1 is not present. So here it is 1. After that's the 4. 4 is present. No need to replace. So that is heat. And after that 2. So which element you want to replace? That is the 3. 2, 4, 3. Right. This is first in. That's why the first out. Right.
Yeah.
That is the miss. And after that's the 3. So for the 3, which is the first in? 4. Right.
Okay.
Here you can see the difference.
Because 4 came earlier, even though it is still there.
Yeah.
Okay. Okay. Got it.
So, but here you can see the replacement happen here only. I think the very next step here, we replacement 1, not 4, right? But here we replace 4. Got it, right?
Got it, sir. Thank you.
So any other doubt? Anyone have any doubts regarding this today's discussion? If there is no any doubts, then we can wind up the session. Okay. Thank you everyone.
Thank you so much, sir.
Hello, sir.
Yeah.
So block size, can you explain?
Oh, yeah. So there is already I wrote yesterday about the block size. What is the block size and what is the sector size, right? So you know about how to calculate the sector size, right? So block size is depends upon the file, right? Whenever you write any file into the disk, right? So
Yes.
write any files the disk into, then the block size will be determined by the operating system, right?
Okay.
Okay. So in simple word, you can say the block size is in the multiple of the sector size. So suppose these are the sector 1, sector 2, and the sector. So you consider you write something in the file from OS is write some file in your the disk, means magnetic disk, right? So you define this 3 sector as the block, 1 block. So if I want to read next time from this file, so if we read the whole block as the 1 unit, for the operating system, right? I got some differences. What is the difference of block and when we refer the file, then we can say as that is the block size, and when that is a refer with the magnetic disk, that is the sector size. So both are the small unit for how to read the data or write the data into the disk.
Block size cannot be smaller than the sector size.
Yeah.
So
So
this is regarding
otherwise
the graded question
it
8.
got fragmented. Yeah.
This is regarding the graded question number 8, week 8, graded question number 8. That one, that question we have to find the block size, but I
think all of you got the idea, right? Definition about the block size and the sector size. Yes or no?
Block size can be a fraction. It should be a round figure, right, of the sector size.
Yeah, sector is this is the physically we stored, right? Physically stored in the data, this sector size.
You can have 3
So,
times, 4 times, 5 times of sector size as block.
Yeah.
You can have 1.5 or 2.5 times.
I not got your point.
Means we cannot have 2.5 times sector size as a block. This is not possible.
No, you want to use that thing, so whatever's the block size you defined, right? You use that thing for some purpose, right? So you design for your convenience, right? So how you can design so that it can be used, right? So if you design any sector, whatever some students said, if you design some sector or the record size is greater than the sector size, right? So for read one data or one record, you have to go for the two sector, right? So that you not want, right? If you want to access the one sector, it may be possible in one sector contains one or more record, right? That may be possible, but one sector means once the sector record size is not greater than the sector size. That is the concept. Any other doubt? Hello. Thank you. Thank you, everyone.
Thank you.
Hello, sir.
Hello. Yes.
Sir, can we ask the doubts from the week 7 now?
Yeah. What you want to?
Sir, for the graded assignments, we can't see the solutions for the practice programming. Is there any way we can see the solutions?
You want the graded solution, right?
Graded as well as practice programming one, the coding one.
Okay. Can you post this thing in the Discord so we can?
Okay.
Yeah. Please post it in the Discord.
Okay, sir.
Yeah. Thank you.
Yeah, thanks, sir.